So, good morning, everyone. Today we are going to look at the transformer. So, we can write the topic transformer. Okay, yeah. So, first we want to know the what is a transformer. This is a device. So, usually it is called a stationary device. So, you can call this is an stationary device. So this stationary device it transforms the electrical power from the one circuit to the another circuit without changing its frequency. That is a actual definition for the transformer. So changing the electrical power, changing electrical power from one circuit to another circuit. So in general, this is a transformer definition. So it will transform the alternating current with the low voltage into high voltage from the one circuit to another circuit. Then you can call this is a step up transformer because usually the transformer having two coils. If you are just to look at this diagram here, yes. So this diagram if you are looking at, it is having two coil. So this is the primary coil, the first coil. This is secondary coil. There is an core, the transformer core. So this setup is called transformer. So the voltage setup in the primary coil is a primary voltage. The voltage setup in the secondary coil is a secondary voltage. Suppose if the voltage, if there are two kind of transformer. One is a step up transformer. So the first kind is step up transformer. So what do you mean by the step up transformer means if the device converting the low voltage in the primary low voltage uh, in the primary to the high voltage in the to the high voltage in the secondary coil, then this type of transformer called step up transformer. So the next type it is a step down transformer. So step down transformer. So what is a step down transformer? One can ask. Suppose if the primary voltage we can call it a primary VP. It's a primary voltage in the primary coil. If it is greater than the secondary voltage, that means it is converting the high voltage to the low voltage, the transformer. That kind of transformer is called the secondary transformer, sorry, step down transformer. So there are two kinds now we saw. Now we can just want to know what is the construction of the transformer. So the next part is the construction. What is the construction and working of the transformer? Here, the construction, if you look at the construction, the first one, it is having the primary coil with the n turns. So you can call the np is the number of turn in the primary coil. Look at this primary coil. So this is one is a primary coil. It is having n turn. So you can call the number of turn in the primary coil. It's equal to np. Now the secondary turn on the other arm of the transformer core. So secondary coil is on another arm of the transformer core. The number of turn in the secondary coil is ns. So here usually np represents the number of turns. Here ns represents the number of turns in the secondary coil. Here there is the sheet, the metal sheet. Usually, this metal sheet is called transformer core. We will discuss about this transformer core, transformer. So the transformer core, usually it is made up of metal, but it's a magnetic material. It's good. Usually, it's made up of good magnetic material. Good magnetic material, like you can most of the time they will use like silicon steel because it will act as a good magnetic material. Silicon steel, why it is made up of good magnetic material means the magnetic flux generated by the primary coil, it has to be, suppose if the magnetic flux number of lines is pi b in the primary coil. Suppose how it will generate the magnetic flux, if you one can ask means already we know the electromagnetic induction. When the primary current or the current setup in the primary coil, if the current is an alternating current, then there is a change in voltage. This change in voltage causes the flux change. This flux will magnetize this transformer core. If the number of lines in the transformer core linkage, how many lines will be there, the same lines it will be linked with the secondary coil. That means there is no loss in the flux linkage with the secondary coil, because usually what would happen means the magnetic field lines losses can happen due to the air. But if we are placing the metal sheet as a transformer core, if it is good magnetic material, the number of lines set up in the primary, it will be linked with the same number of lines with the secondary. Suppose if you're using the right hand rule here, the right hand thumb rule, the alternating current goes like this, then coming out of the coil like that. What would happen? The flux will be, the thumb should be pointing upward, so that should represent the north pole. Then the opposite is to the south pole, so the flux will be looking like that. In general, it will be at the center of the circular term, so it will magnetize this flux. The generated magnetic flux, it will magnetize the material. So this magnetic field, it will be circulating like that. Anyway, the alternating current will change its sign. So how many number of lines it is generated due to the primary coil, the same magnetic field lines is linked with the secondary coil. That's the purpose of the transformer core, because each and every atom in the transformer core, it will get magnetized. Usually it's made up of steel, so iron will be a good material. Even silicon, the doped silicon, it will be also good material for the transformer core. This is not a single sheet, it's a transformer core. It's made up of the number of sheets. It's several sheets will be there. These sheets are laminated from each other, as well as the coil, the number of this copper coil also laminated. That means due to the eddy current, it will reduce the eddy current loss while if you are laminating the transformer core as well as the primary as well as the secondary coil. So that is the purpose of the transformer core. Now we will see the working principle of this. Working on the principle of the this transformer. So first we will see the principle. So one can ask what is the principle. The principle of the transformer is the mutual induction between the two coils. That is the principle. Mutual induction between the two coils. This is the principle of this transformer core. When the electric current passes through the coil, changes with the time, the EMF is induced in the neighboring coil. That is the main actual mutual inductance. What is a mutual inductance means? Suppose if you are taking the primary coil here, I am just showing it here without any transformer core. If you are setting up the EMF in the primary coil, that means if the current passing through the primary is IP, so the voltage across these two ends is, if it is VP primary voltage, what would happen? It will generate the flux according to the right hand thumb rule, even if it is an alternating current. So this it will generate the flux. So the flux according to the right hand thumb, it will be the flux will be closed circle, and we know the properties of the magnetic lines. It is curling, but it's a closed circle. Suppose if you are keeping that the secondary coil near to the primary, you can call this as a secondary coil. What would happen? This is an alternating current we are giving to the primary, so it will change the direction with respect to time. That means initially the flux will be going up, like IP is alternating current means IP equal to some I dot maximum amplitude of the current times sine omega t or cos omega t. At time t equal to 0, if the current is 0, then as the time moves on, then the flux will grow up to the maximum omega t. When omega t is equal to pi by 2, it will be maximum. Then again it will be omega t equal changing to the pi. Then the flux will be in opposite direction. It will keep on decrease. So so the flux will be in same direction, it will keep on decrease. But omega t, if it is 3 pi by 2, if it is growing other direction, the flux will be growing in the negative direction. So there is a flux changes associated with the secondary coil. So whenever the flux changes will be there, then it will set up the induced EMF in the secondary. So it's a d pi by dt, the flux due to the primary. It's a EMF setup in the secondary ES you can call. So then there is an current will be generated due to the flux changes here. The induced EMF is set up. Then we have the current second the secondary coil, that is called a mutual induction. Already we studied this principle. This is the main principle of the transformer. Now we can ask one question: what is the working? This is the principle. Now how it will work? How we can take the output? What are the benefits of this transformer? This is the thing we are going to see. Suppose if the primary coil is connected to the source of alternating voltage, just you can take this picture once again. Here we have the picture. If the primary coil, this is a primary coil. If you it is connected to the some alternating voltage source. Suppose if you are connecting the this alternating voltage source, that means the voltage is changing with respect to time. You can represent as a function of sine omega t or cos omega t. So you can just take an is already here I here represents I equal to I sin omega t. You can just use it different symbol because or cos or sine whatever it is. Anyway, it's changing with respect to time. It's a sine function. Uh, so if it is changing with respect to time, then there is a flux in the Lagrangian transformer core. That means the flux will be magnetize this material. So if the current is going in according to the right, and suppose initially if the current is maximum, I think if it is the current usually will draw using the sine function. Suppose at time t equals 0, the current will be 0. If the time grows, then I equal to omega t equal to pi by 2, the current will be the maximum. Then again it will drop to 0 at omega t equal to pi. This is omega t axis. Then if the omega t is 350 negative maximum, then omega equal to 2 pi, it will be again minimum. It will just alternating, and that means it will change its direction. So as the times grows on, there is alternating current. Suppose at the time t equals 0, its current is going in the positive direction. That means according to the right hand thumb rule, the flux will be set up in this core. This will magnetize this the core atoms. So it will magnetize the core atoms. So how many number of flux will be produced in this transform core? The same number will be linked with the secondary coil. So you got to just to close this one. So if the number of flux in the primary, if it is, you can call pi b. The secondary also, it will be, it is having the pi s. That means the flux changes because the current is going to be changed. Then the flux will keep, first initially it will keep on increase up to pi by 2 when omega t equal to pi by 2. Then after pi by 2 to pi, it will keep on decrease, but it's in the same direction. Then after crossing the pi, the flux will be grown in the other direction. That means when the pi equal to pi by 2, the flux will be in this direction. So that means the number of flux line it's keep on change. So keep on change with the secondary. So there is an induced EMF in the secondary coil. So first, if you are representing the primary induced EMF, it's equal to, in general, for the single turn, it is d pi primary flux divided by dt. If you there is a negative induced EMF, because the induced EMF it will create the own EMF, and because the flux changes, it will create the back EMF on the primary. So that's why it's a negative sign. It's according to the Lenz law. Suppose if you have n number of turns in the primary coil, then in the general induced EMF, you can the number of flux is produced due to the primary. It is n time the pi p. So you can just, if you are substituting this one, n is just a constant, the number of turn in the primary. So d pi primary divided by dt. This is the induced EMF in the primary coil. Now, but the voltage across the primary is equal to the back EMF. So because whatever the voltage we are giving, that will generate the number of flux line that will give the back EMF at the equal amount. So you can call the back EMF, if it is Vp, then this Vp equal to Ep, that is induced EMF in the coil, that would be equal to minus Np times d pi p divided by dt. But here one thing we got to notice, it won't change the frequency of the field, change the frequency of the changing the field, because as number of cycles change with respect to, because initially it will set up in the clockwise, then counterclockwise, then clockwise. This number of changing direction with respect to unit time, it will be the frequency of the output current. So that frequency it won't change in the secondary, because the flux changes linked with the primary, the number of flux it will be omega t. So if omega t, if with per unit time, if it is changing to 100 cycle, then the flux changes here also is 100, then that emf produced in the secondary also it will be 100. So you can call the frequency of the induced emf in the secondary, it will be same. So the secondary coil, the number of induced EMF is equal to minus the number of turns time the flux t pi b divided by dt. Here in general, why we are taking this, the primary flux that should be equal to secondary flux, because number of flux line it won't change, so equal to pi b. So here also you can just use it instead of pi, you can use it, this is pi b. Now if the secondary circuit is open, then because the secondary circuit is not closed, so if it is open, then whatever the induced EMF in the secondary, that will be equal to EMF, the voltage drop across the secondary. So you can call the secondary coil voltage. You have to keep it the secondary coil as open. Just you have to watch this diagram. If this is open, this is open. So whatever the induced EMF here, whatever the induced EMF in the secondary, this is ES, that will be equal to this voltage, secondary voltage. So Vs equal to minus the number of turns in the secondary coil, the rate of change of the flux. Now we know already from that, if you are just dividing these two equation, if you are just taking this is the equation number 1 in the primary, this is the equation number 2 in the secondary. If you are dividing this 1 divided by 2, or what you have, the left hand side is Vp divided by Vs is equal to minus Np d pi p divided by dt divided by minus Ns dp by dt. You can cancel these two negatives and negatives, and also you can cancel. You can just have Np divided by N. Yes, this should be equal to some k. So the constant k, we can call it as transformer ratio. So the k is called transformer ratio. So we know the how we can calculate the power. Suppose if the input power, if you are taking it as input power, the voltage time, the current, voltage is Vp, current is Ip. This, in general, this unit will be equal to power unit. So this is the input power. If you are taking the output power, again the same product, but instead of P, you have to use the subscript as. So that subscript be a secondary voltage time secondary current. For the ideal transformer, the number of flux linked with the primary is equal to the secondary, so the power will be equal. So you can call Vp Ip is equal to Vs Is. Using this relation, Vp divided by Vs, suppose if you are rearranging, then you will have Is divided by Ip. We know already from the P divided by Vs is equal to Np by Ns. That is the transformer ratio. So if you are substituting Np by Ns. So this is a relation. It will be useful when we are calculating the primary as well as the secondary voltage. This is a case for the ideal transformer without just adding anything. So the first thing we want to note it down. Suppose example case 1. Here we can finish it up. The case 1, if the number of secondary is greater than the number of primary coil, you can look at the relation. If the primary is greater, compare the secondary, then primary voltage is greater than the secondary voltage. That is a relation we can have it here. So this will tells us Vp is greater than Vs because Vp is proportional to the Np. Vs is proportional to the Ns. The Np is greater, definitely Vp will be greater, then Vs will be lesser. So that means this kind of transformer it will act as a step up transformer. Yes, the voltage across the secondary is sorry. This is Ns is a few correction. If the Ns is greater than Np, then Vs should be greater than Vp. Sorry for the misconvenience. So here that means if the number of turn here look at the same diagram, the number of turn it will be looking like a concentric circle. So here Ns is greater than here Np the primary coil. That means the number of lines in the secondary coil will be greater than the number of lines in the primary coil. That means the according to this relation, if the Ns is greater, definitely Vs will be greater compared to Vp. So you can call the voltage setup across the secondary is greater than the primary voltage, and definitely the current in the primary will be maximum compared to the secondary according to this relation because it is inversely proportional to the voltage is inversely proportional to the current. Then this case, this transformer because voltage is higher in the secondary, that is the relation it's giving here. The secondary coil having higher voltage compared to the primary coil, then this kind of transformer we can call it step up transformer. The case 2, suppose another way if you are thinking, if the primary turn will be greater than the secondary turn, definitely using the same relation, one can show the primary voltage is higher than the secondary voltage. In this case, the secondary current will be higher than the primary current. So this transformer is reducing the voltage at the output. So you can call this is a step down transformer. So these are the two things we want to conclude here. Then the one more stuff we want to know how we can calculate the efficiency of the transformer. The last one, the efficiency of the transformer. So how you can do the efficiency of the transformer means it's defined as the ratio of the output to the input power. That is the important. So you can call efficiency output power will be how much amount of we are giving input. We have to compare with respect to input power. This is the efficiency. Suppose the efficiency percentage, if you want, you got to just multiply by the 100. This is the transformer efficiency. Transformer highly efficient devices having their efficiency in general, all the usual high efficiency transformer, the efficiency range in between 96 to 99%. So why this why we can't get the 100% efficiency means that the various energy losses will be there. That's why we are getting in this range due various energy losses will be there. So that's why we are having less than the 100. So we can have the ideal transformer here. Thank you.